All right, let's dive right into this explainer. Today, I'm putting on my senior engineering lead hat because we're talking about something absolutely crucial for all of you developers out there. We're looking at a recent inverted pendulum project, specifically how to safely integrate agentic AI, like Claude Code and the Simulink Agentic Toolkit, into a rigorous design process. We aren't just talking about using AI to write a few Python scripts here. We're talking about using AI to control a physical system. In this case, a Quanser cube servo, which is a real physical inverted pendulum. This is safety critical, it's complex, and honestly, it requires a very mature approach. Listen, we need to clear something up right away. You've probably seen those viral posts of people generating entire software apps over a weekend just by talking to an AI. That's called vibe coding, and hey, it's fun. But asking an AI to blindly write code for physical hardware, that is a dangerous trap. It's so tempting to think, why not just open a coding agent, tell it to balance a pendulum, and let it figure out the data sheets? But when you're dealing with physical hardware, you have severe physical limits. If you vibe code a web app and it fails, you get a 404 error. No big deal. If you vibe code a physical pendulum, the control loop might run way faster than the hardware can execute, safety limits get completely ignored, and bam, actual physical damage. The stakes are simply too high. So to avoid that, we're going to follow our proven engineering workflow. We'll quickly walk through the vibe coding trap, defining clear system requirements, using AI and model-based design, testing early and often, deploying to physical hardware, and finally, the golden rule of AI. All right, step 1, the vibe coding trap. This is all about avoiding that situation where you end up with an unverified blob of code and you have no idea what you've actually built until something physically breaks. Moving right along to step 2, defining clear system requirements. Before we just start firing off prompts, we really have to slow down. We need quantifiable goals. These are our very first inspectable artifacts. They give us the exact baseline we need to verify the AI's work at the end of the project. Think about it. How quickly should the pendulum spin up? How fast must it settle? How much wobble are we physically allowed to tolerate? We're setting strict limits here. For example, we absolutely cannot exceed motor commands over 12 volts, or we're going to fry the servo. And practically speaking, the code itself has to actually fit and run reliably on a Raspberry Pi. So we feed these overarching goals to our AI agent and have an iterative back and forth to get these parameters crystal clear. Okay, step 3, using AI as a co-pilot in model-based design. Once our requirements are locked in, we make sure the AI acts as a collaborative assistant, not some black box creator. We do this by giving the agent access to trusted, validated tools, like the Simulink Agentic Toolkit. This means the AI actually reads, understands, and interacts directly with our visual models. Instead of the AI trying to invent a custom mathematical integration function from scratch and probably making a mistake, it just grabs the verified pre-existing integration block right out of Simulink. It saves tokens, and more importantly, it saves us from chasing down phantom bugs in the AI's custom math. In our project, the agent actually used Simulink to successfully linearize the model around the balance point and perfectly explained the 4 mathematical poles to us. Pretty cool, right? Now, if you take away just one thing from my mentoring today, let it be this. Do not let an AI invent an optimizer from scratch. We told our agent to use the deterministic algorithms in the Model Predictive Control Toolbox. Why? Because we need inspectable parameters, not magic. By pointing the AI to an established toolbox, we know exactly what algorithms are running under the hood. If the pendulum starts acting crazy, we can manually open the model, inspect the parameters, and tune them ourselves, or instruct the AI to tweak them using those exact same tools. We maintain total control. Which brings us to step 4, testing early and often to catch errors safely. With our controller designed, we literally walk the agent through a very specific sequence. First step is model in the loop, or MIL testing. We simulate everything purely in Simulink to make sure the controller actually balances our virtual pendulum. If that passes, we generate the embedded C code for software in the loop, or SIL. This runs the real embedded code, but safely on our dev computer to ensure it matches the simulation perfectly. Finally, we run processor in the loop, or PIL. That's where we put the embedded code onto the actual Raspberry Pi, but have it control the virtual pendulum. We get to verify runtime requirements and assess hardware safety without ever risking a physical crash. Now, I literally cannot stress this enough. Relying on trusted code generation workflows is absolutely crucial here. If you just ask an LLM to generate C code directly from a prompt, you're gonna get a different implementation every single time you run it. It's a complete wild card. But by having the AI build a visual model using verified blocks, and then using Simulink's deterministic workflow to generate the code from that model, we guarantee consistency. The same design produces the exact same code every single time. Every single piece of that embedded code can be traced directly back to our original requirements. All right, we've made it to step 5, deploying our code to the physical hardware. So here's where we hit a massive reality check. Our highly tested code passed every simulation flawlessly, but when we deployed it to the actual hardware, it failed. The simulation assumes a perfect mathematical world, but out in hardware reality, the physical pendulum had unexpected friction and little mechanical discrepancies that our pristine model just didn't account for. So what do? Do you just abandon the whole process? No way. We went right back to the drawing board, had the AI agent help us analyze the physical data, updated our model to account for that real-world friction, and cycled it back through our rigorous testing process all over again. And that hardware divergence perfectly illustrates our final point. Section 6, the golden rule of AI. Here is the bottom line. AI is an incredibly powerful assistant, but you must remain the engineer. You have to force the AI to produce artifacts, like your requirements documents and visual models, that you can actually inspect and modify. You have to guide it step by step, instead of relying on massive one-shot prompts. Make sure it reuses trusted, validated components rather than inventing its own logic from scratch. And absolutely never let the AI bypass your safety-critical testing loops. If you enforce these rules, you get all the amazing speed of AI without ever sacrificing safety or your understanding of the system. So I want to leave you with a final thought for your next project. Are you using AI to bypass your rigorous engineering workflow, or are you using it to accelerate it? Agentic AI is an incredible tool that can drastically reduce your dev time, but its true value in embedded engineering entirely depends on how you manage it. Don't vibe code your hardware. Accelerate your proven workflows, maintain your standards, and build systems you can actually trust. Thanks for joining me for this explainer, and I really can't wait to see what you all build next.